Okay, welcome back. Parts of Cohort 7. Um, we're in 3. So, beginning in 3. Is there anything that anybody wants to begin with? Like any overall thought on 3 or any place to start?
I guess I was a bit slow with the recap of the chapter here, but one thing at least that I thought a bit about while reading it was, and I guess not unique to this chapter, but the preceding ones as well, is the interesting connection to other domains. Mentioned like the physics and the activism and cybernetics and all of these different ideas, and also like how it seems as if active inference has evolved over time and emerged from all of these ideas and like the connection between it, which I think seems very I think is very interesting. And I was just wondering if there are any resources with someone that has like mapped up the connections and perhaps like evolution of the ideas over in history, so that you can get like a good overview of how this has evolved and is connected to other areas, and perhaps like even what different assumptions and applications go into it.
Yeah, that's a great suggestion. I mean, you, you mentioned kind of like a historiography, like bibliography tracing, but then also like the claims and the rhetorical assertions and understanding which claims um transferred. It also kind of reminded me of this. Um, I'll put it here, but this in the complexity sciences, this one graph. I mean, even though it's just one partial representation, becomes quite popular even though it's just a subsample of the tip of the iceberg of one person's representation of one way to view it, but then it does give some coherence, um even just from chapters 1 and 10 of the textbook. It could be possible to pull out some of these kinds of threads. And then what's
Yeah, that'd be
interesting is
super
it,
cool.
and it's like, how different would it really be from active inference? Mathematics of complexity, systems and complex systems, network science, cybernetics. Maybe there's information theory here somewhere. Artificial intelligence, so agent-based modeling. So I think it would have a lot of similarities to this, but I agree. Yeah,
Yeah, super cool. I'll check that link out. I guess he has some resources in the book, like the table 3.1, for instance, but also from like chapter 2, the figure um, which one is it? 2.6 as well, which I think have like quite nice connections to.
one kind of history crossover moment from the last Friday. This uh model stream 13, synthesizing the Born rule with reinforcement learning. So they're coming from a um quantum measurement empirical setting. And then as they started to relax certain assumptions and try to generalize the Born rule, they got into the generalized sensory motor interface and the sort of generalized cognitive setting. So that's like a low road generalization. And so we had some interesting um, crossover moments where like they're in the laboratory measuring these quantum collapses, and then they've converged upon where from active inference it generalized into the quantum over the last several years. But then, so there could be cool ways to go. Any other random thoughts on 3 or the high road? I mean, that's kind of what 3 is about. 1 just opens the book, just like 10 closes the book. 2 took us on the low road. Now 3 is going to start from up here and come back down to active inference, so that we get off the slide of chapter 3 and we end up right at chapter 4, where we finally see the active inference generative model. But yeah, any thoughts on high road, 3? Like, just to kind of illustrate that. Um,
Uh,
yeah, go ahead.
The but to me, I mean, it's almost like we're just creating a more granular structure around the Socratic method.
How so?
We've got, agents in an environment, and they're asking questions about the environment and receiving a response from their environment, and then integrating that response into their internal model of the world, and rinse and repeat.
Yes, interesting. There's the Socratic element on that. There's the Hegelian element on that, and like all of these more like composite frameworks where like it doesn't seek to reduce situation down to just like a monad unity, but to a dialectical unity. Are there other aspects to the Socratic method? Wonder, reflect, refine, and cross-examine, restate, repeat. This connects, I mean, to the active inference ontology. What is surprise? Or, these are the kinds of questions, and these are like a playbook. What does the book mean by novelty? Why would they think that the KL divergence is the way to do this? Is the KL divergence the only way to do this? There's a nice build up towards 3. In chapter 1, this is kind of the minimal agents niche figure ground, like 2-part partition. That gets nuanced into kind of like a 4-state partition. We have a true internal and external, and then there's 2 aspects to the blanket, or you can kind of collapse those 2 into one blanket. And that's where the Markov blanket concept initially was just like it was one blanketed node. And then one of Friston's novelties to adapt the Markov blanket concept into the cybernetic setting was to kind of split that blanket or interface into an inbound and an outbound. So that's where we get the 4. But here it's still framed as like they're just 4 variables, like in a program. In chapter 3, it picks up with those 4, and now they're defined in terms of flows, like the dot being a derivative. So now there's like 4 simultaneous flows on this fourfold partition. So that is coming more from the Bayesian mechanics, but that just shows like it's like chapter 1 is the parent of both 2 and 3. And then chapter 2 goes more of like an engineering program way of doing this. Like, well, what are the variables? Like, what are like, what's the local computer state, the remote computer state, and then the descending to and from state. Here's more of that physics way to see it. We can look at this figure in context, but this is kind of like showing B is the blanket, X is for external, mu is for internal, kind of like maybe mu for mind for M or something. But it's like saying if you have like a just to make it big numbers, if you have a 0.5 correlation between internal and blanket and a 0.5 correlation between blanket and external, then you're going to end up with a 0.25 correlation between internal and external, just because it's kind of like it's 2 hops and each one has a 0.5 correlation. So that's kind of how you end up with correlations across a blanket because of kind of like the chain rule of partial correlations. Any other random thoughts on 3, or we can look at the extant questions, or we can look at the text. This is one of. Oh yeah, go ahead, Jeff.
The one thing that I think, and again, we being stuck here in the forward arrow of time, Melvin Vospin has developed the theory of infodynamics, which is a corollary to thermodynamics, and I feel that there's overlap here. And I can't be more specific than that, but I can link the article. And I don't know, maybe somebody wants to take this and run with it, or maybe I will at some point.
Okay, I remember Ali in a characteristically Ali styled. Terence Deacon has touched upon the infodynamics. It's kind of like the data, information, knowledge, wisdom, like kind of, but it's a little bit different than that. But it's like, what are sort of the syntactic dynamics of information, like at the sensor processing level, and then as you move into more semantic levels of informations, how does and then Deacon highlights that those higher levels they are dealing more and more explicitly with like adjacent possibles rather than processing what is like immediately there. Like you can't understand the higher levels without also considering like this kind of like as yet unmanifest shell of, which is kind of like when we get into action planning. That's a classic example. Like most plans will not happen, yet the expected free energy still kind of considers them. But in this question, we'll see if the question if the actual maybe the real questions will be addressed. But this image, this is from one of the earliest, like pre-2010 winged snowflake. So here, temperature increasing is going down. So it's colder higher up in this image. And this is like the actual sky. So it's like it's colder higher up, and then like closer to the ground, it's cooler. So there's some critical temperature under which, from an elevation perspective, like the snowflake is going to melt. Above this level, it will persist as a snowflake. So if it was a inactive snowflake, and then let's say you started with a cloud of like a bunch of snowflakes that were high up, then you just would have diffusion. So you wouldn't need to propose any kind of action selection. It would just be like, if there was laminar flow, all the snowflakes would stay up here. If it was going straight down, all of them would fall down. Like that, you wouldn't falsify the hypothesis that it was just like a particle. And then what you see with like life is you see action that acts as if, I mean, if you came back millions of years later, then you'd be seeing snowflakes that would be acting as if they were staying above that temperature threshold, because the ones that didn't have kind of crashed out. So this is like showing up in a population of actual negentropic organisms, and they've been fighting death, even without getting to reproduction, stuff like that. But that was an early physics inspired way to think about survival. But this could be a blood sugar critical threshold, temperature critical threshold. Okay, quick.
Cool.
Yeah, that's a fun one of the early fun representations.
Where was that from?
Um,
You know?
let's just look up what it's like. Maybe a 2006 Friston paper.
Okay, cool.
Not that kind of snowflake. 2006.
Yeah, I can look it up.
Yeah. This 2006 paper with Kilner and Harrison. Yeah, here's with a different notation, but we see a lot of the same input and output. And then here's like 3 levels. Like this is kind of the fast inference layer. Then there's the slower attentional neuromodulation layer. And then there's an even slower topological change, neuronal connections. So it's like already those kind of nested timescales of inference, because those were already being considered in the fMRI SPM setting. Let's see what else is in this paper. This kind of looks like a heat engine, kind of like a duty cycle on an engine. Cortical columns. It comes back in the book. Generative and recognition directions from pixels to planning. That's like the most recent paper, but I mean, here we have pixels and still that same kind of minimal case. Already kind of highlighting fMRI and repetition suppression. And those are some of the robust EEG and the fMRI type findings, like in different populations of people. And then like when the mismatch negativity and the 200 millisecond tone and all those kinds of things. Yeah, pretty interesting. Almost 20 years. Okay. First question is about a Markov blanket in time. So, okay. As usual, attaching a last name to something does not always add information because it doesn't do anything other than just make sort of a historical illusion. But this is the Markovian property in time, which is basically that the past only influences the future through the present. So it's like the current state of the program influences the next state, and anything prior to that gets distilled or like projected onto the present state. That's that's a Markov chain. And then if there are like two time states of time dependency, then it could be like a one Markov chain with two time steps. Like if your last two moves were up, up, then here's where that transitions to. So even if it is like multiple time steps in the simulation, you can still kind of model that as a one Markov chain, or you can model it with multiple time steps. But then people also have broader questions like, without knowledge of the present, what can you do? Say two. What is a statistical rather than a non-statistical interaction? We're talking about a statistical model. So all the interactions which look like edges on a Bayes graph are statistical interactions. Then it's an interesting question. What would make a non-statistic? Maybe that's the real, quote, real interaction itself. And then third question, why does independence between the flows on the two sides of the blanket matter so much? It's a complex question, like matter so much relative to what? Internal and external states, they can you can set it up so that they have total influence on each other. So it isn't that it's that the blanket isolates, it defines how they articulate, and then it could depend a lot or not. But I think a key piece is that their random fluctuations are kind of buffered from each other. Like they're getting the noise is getting at least the noise are orthogonal. They're being like randomly sampled from noise, but that may or may not matter in a certain situation. These are great questions. There's kind of these cousins of closely related terms. Like, of course, we have active inference, but then we also hear about Bayesian brain hypothesis. That's in figure 1.2. And then there's predictive processing, predictive coding. This was a question that we asked of Friston in 2018. And I think the answer has also kind of sharpened since then. You could have a situation where all of these were in play. You could have an active inference system that was brain-like being described by Bayesian brain hypothesis, where the processing that it was doing was based in terms of prediction and anticipation and all of that. And the messages being passed between layers reflected predictions and their discrepancies. So all four of these could be in play. Or you could have situations that kind of nuanced that. But they're more similar than not. Predictive processing highlights making predictions, which is almost without a space between with the Bayesian brain hypothesis, because that's kind of what a prior and observation are. Predictive coding sometimes is used just equivalently to predictive processing. Other times, and this is explored a little bit with Maria in the live stream 43.0, and she studied some of the philosophy of the predictive processing. Predictive processing can refer to like the fact that the whole cognitive stack does this predictive processing, whereas predictive coding is more of a sub-hypothesis that the messages that are transpiring between layers are encoded in terms of the predictions, but some other type of message format could be passed. Active inference amongst all of these highlights like the role of action. Whereas Bayesian brain hypothesis, it could be a passive Bayesian brain, but again, it could be an active one. And predictive processing predictive coding, a lot of those models were sense making only, but you could consider making predictions to be like a kind of internal action. But then those types of models generally earlier were not considering like eye movements. But once you get into the sense making for what the retina sees in a moment, and the choice of not just what to predict at the next time step, but where to move your eyes and what to predict when you move your eyes there, then that gets more into the full active inference setting.
So yeah, that's a question I've thought about many times. So it's great to get some more meat on that. But I specifically wondered about the like overview picture or overview figure of the low road and the high road, where predictive coding is specifically on the low road and predictive processing on the high road. If I didn't mix them up now, could you perhaps explain why? Yeah, why they're separated like that? As to put some more meat on it.
Sure. No, I mean it's a great observation. Predictive coding down here. Yeah, first off, unlike a subway map, it's not that these are like strictly prerequisite in a certain order.
Yeah.
So that's kind of interesting, but it's not that this is like the only final representation, but predictive coding, it could be argued it's an information optimal way to send messages about predictions within a system. So when doing this kind of perceptual inference, it's like, let's just say that we were doing a measurement scale, and we're measuring cars. They're 1,000 pounds. We expect them to be 1,000 pounds. We could perhaps most parsimoniously report like -3 if it was 3 below, or +7. So it's like that's smaller than saying 997, 1,007. So this could be as argued as kind of just like a model, as a sort of like an intra-model strategy for information theoretic optimal transmission of information about predictions. Whereas predictive processing, one which I don't think it'd be ill fit on the low road, because we're talking about Bayesian brain and stuff. But one reason why it could be put on the high road aims to start with minimal assumptions other than a persistence, either a self-observed persistence like survival, or a sort of measurement type persistence like a experimenter observing something repeatedly. So in that situation, you don't know what is happening necessarily amongst the elements of what you're observing, but you could say it evinces behavior that it is doing something. Like when the nest mates come to the surface of the ground in the morning, just as the sun is dawning, we don't know how they're sending information within the colony, but it's like they're predicting that it's about to be the right time to forage. So whatever this thing is, we don't know what it is, but it's acting like it's predicting what's happening.
Great, thanks. Thanks.
The ordering is there's a lot of it's like the slide some game, I forget what it's called, but it's like where somebody else makes the slides for you, and then you have to do like a lightning talk with slides in a random order.
Yeah.
Yeah.
No, because I definitely, when I looked at it the first time, I definitely read it as a subway map. But yeah, when I looked at it, the more I was like a bit confused about the motivation between putting it like that.
Here were some of the awesome slides from Maria with the history of the perception and about how it's an ancient from antiquity to the the idea that pre-existing information structures sensory data. Then where the book kind of picks up is with Helmholtz, and that's sort of this like hypothesis testing. Then that sort of like hypothesis testing idea finds a more natural fit with Bayesian epistemology rather than, for example, scientific positivism or scientific falsification approach. So it's not that we're just like seeking to lock in a fact about observation or seek to lock in the rejection of a hypothesis. It's more that there's just this like envelope or portfolio or distribution that's getting updated. And so that aligns more closely with the Bayesian methods than with kind of rule it in positivism or rule it out falsificationism. Okay, 3.2, I think it'd be a cool thing if we maybe now it'd be easier. We could paste it into an LLM and just say generate the code for this. But it's just showing that you can have chains of partial correlations. Like of everybody where A happens, 50% B happens. Of everybody where B happens, 50% C happens. What percentage of A had C happen? And then you can just multiply the probabilities like a chain. Oh. If one defines preferred states as expected states, this is the book, then one can say living organisms must minimize the surprise of their sensory observations. I'm not clear on the ontology here. Is it that preference is the same as expectation, or formally we can use them in the same equation, or something else? Does active inference make ontological claims, e.g., preference is actually expectation, just as heat is actually excitation of molecules? More generally, is free energy in physics just an analogy or an ontological assertion? This was brought really nicely together in I'm forgetting the first author, but Stephen Francis Mann. P as a measure of both probabilities and preferences. That's where we get pragmatic value. That's the clearest difference from reinforcement learning, rather than the proposal of a totally ancillary secondary reward distribution that's like observations or observations plus actions like Q learning, rather than projecting those onto a reward ranking and then using that reward ranking in this actionable way. The observations directly are going to be compared with a preference distribution, which is a prior over sensory observations, and that does the pragmatic value work. But and then they kind of even talk about how like people will lean on one of those interpretations or another, but they're both equally viable. Is there a minimal example of a thing defined by Markov blanket, such as a cell or some subcellular element? Is a thing persistence of Markov blanket? Are all things non-equilibrium steady state processes? Do we need to be more strict in saying these things are only self-evidencing things rather than things in the colloquial sense? Some work towards that is from this particular kinds, path integrals, particular kind strange things paper, just showing that ranging from inert things to classical simple things to strange and self-reflective things, they all fit within this interface concept. It's really just, what is the modeler's system of interest? And that's also the first step of the chapter 6 recipe for modeling. And it's non-trivial to identify the system of interest. I mean, if you're studying the heat transfer from the engine, you could make an argument that the system of interest should be like the solar system. Or you could say, okay, but I'm only interested in the 99% heat transfer threshold. And then at that point, you might even exclude some of the plastic on the engine. So it's not that there's like one kind of thing, or maybe you're interested in a specific thingness.
I'm reminded of Fields' course as well, Chris Fields' course.
Like in how?
The physics of information processing, right? And how you have to define a thing and really going down to bits being the fundamental construct of the universe. You know, in shoot, I've got the article on my bookshelf behind me, but Art Wheeler, you know, John Archibald Wheeler, It from Bit, right? So, you know, ultimately things are constructed from Planck units, right? So
Yeah. And the bit is like a collapse onto a yes or no question. That's like the simplest question.
yeah.
Okay, I'm even going to look up what these are. Hylomorphism. Every physical object is a compound of matter and form. Hylozoism doctrine, all matter has life. Okay. What is the analogy to friction in a cognitive system? How strong is the analogy? Okay, nothing here. What would anyone say? Like, if we're thinking, okay, the baseball is going to go in the parabola path of least action, baseball's quite massive compared to the air molecules. Still, though, there is friction with the air. Some of that energy is going to be lost to heat. And then if it were in a vacuum, you would lose less energy to heat. If it were in a very thick liquid, you would lose more energy to heat. So this person's asking about how these equations might work well for like the frictionless assumption. Like you know, it's a collision on the frictionless billiard table and no energy is lost from hitting the sidewalls. And then you get a certain play out. But then if you do have friction on the table, it's like everything is getting slowed down because it's getting dissipated. What do you think, Jeff?
I think the distribution curve is going to be wider, right? I mean, if an agent is hungry or dehydrated or any other type of state that impairs a optimal band of processing capacity, then you're going to have a broader, yeah, you're going to have a broader distribution curve. Like if I'm under the influence of drugs, you know, that, you know, make me hallucinate, my ability to interact with my environment is going to be diminished, right?
But isn't friction just included in the Euler-Lagrange questions? Like, isn't that just shaping the landscape of which you find the path of least resistance? like it's about finding the equations of motions, right? And if friction is part of your system, that is going to be part of finding the path.
Maybe with very high friction, does it break down? Also, friction is so close to Friston. It's a classic typo. It's so funny also just reading these. Like, okay, then there's the Helmholtz. But we just saw Helmholtz from the perception as unconscious inference side. But then here's Helmholtz's work from the flow dynamical side. So it's like it was already right there. You can modify the Euler-Lagrange equation by adding non-zero right-hand side to incorporate friction. That's dissipation function. Okay, let's keep it in mind. One thought about the under the influence. Are there any treatments or substances that reduce the variance on performance? Or are is or do interventions always or usually increase variance? Like if you did something just quote normally 100 times, and then okay, now do it with one eye closed, or do it like standing on one leg, or do it when you're really tired. Maybe some of those, or do it on caffeine. But it's like you might be better, you might be worse on average. But then would any of those have a tighter distribution? Or when we change something, do we always make it more variable too?
Seems like it would be very. Oh, sorry. Go ahead, Jeff.
No, go ahead. Go ahead.
Seems like it would be very like dependent on the task as well. But I'm sure that certain interventions would lead to both a higher and lower variance. Like I don't know, if you would take a sleeping pill, that would like reduce the variance of what you'll be doing the next few hours, but would probably increase the variance in your performance on certain tasks. Like I don't know, reading a book or doing something that requires you to be awake.
I'm coming down to instrumentation and augmentation. If I'm, in my natural state, in my body, I'm not going to be able to stay underwater and explore for a very long time. But if I have a mask and a snorkel, then I'm going to be more adapted to the environment. But it is a technological adaptation, not a biological adaptation. And if I have a scuba tank, even more, right? So that is tightening up the curve in terms of my performance in that environment.
Yeah, that's a great point too, is the off source. I mean, if you go on a ventilator or a pacemaker, you could have lower variability in your heart rate or breathing. Or if you had an exoskeleton that was like drawing for you, you would have lower variability, but with kind of cascading externality.
And this comes back to me again to the fields course where, we've got this meso scale where we're naturally inclined to be able to understand and comprehend. But when you look at, things at the, below the classical Newtonian scale, if you look at astrophysics or quantum physics, there is no conjoining or comprehension without instrumentation. So we literally can't even explore those environments without augmentation.
Yeah, well, it's like you all like let's just say the baseballs are flying around in the dark room. We can just put on a strobe light, take a picture. We can say, well, the photons of our strobe light probably didn't influence the baseball that much. That's why it's classical. But then, yes, when you get into things that are on that scale, all of a sudden it's like it goes from not mattering, barely, 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 and then all of a sudden it's like it overwhelms. When you're studying things that are at that exact scale, then your instrument becomes as big. I mean, it's like your thermometer has a certain heat capacity. So if you dip it into one molecule of water, you'd have, in order to get an accurate read on that temperature, you would have had to already know the actual temperature. Otherwise, you would be getting a compromise between the temperature that it really was and what you thought it was. But you
It's
wouldn't
funny.
know. Yeah.
It's funny because I was just reading about from economics, I was reading about Jevons paradox, which is that the more efficient a system becomes, the more or the more efficient you become in resource extraction from an environment, the more you're going to use that resource, and then it can cause it to collapse. So, like if I think an example is the EPA requires higher fuel efficiency on cars. So because of the higher fuel efficiency, um, you people wind up driving more because it's cheaper to drive, and you're actually putting out more pollutants into the environment than you would have otherwise.
And then another car related one would be like adding a lane to the freeway. And then people think, oh, great, now there's more
Yep.
lanes. And
Oh
then,
yeah, capacity planning for highway, it's huge, right? Like you look at Houston or anywhere where they do widening, and it just stays. It's actually that they're incentivizing people to get in cars more, and not realizing that it's going to cause, friction or eventually collapse, right? In the end, it's collapse, building systems that have if you look at how the Khmer civilization fell, it was because they created all this wonderful um, water management systems, and it was very, very brittle. And as soon as they had a drought or a flood, then they didn't have water, and then people literally just died from dehydration. So, and the other thing from a car perspective, right? We can look at it at many scales. Me driving my car independently doesn't do much in terms of pollution, right? It's not really measurable in terms of the scale of the Earth's biosphere. But everybody driving their cars has absolutely a measurable impact. Thank you all so much. See you next time. I've got another.
peace, Jeff. Frank, do you want to bring up anything? Hmm. Last point on kind of the friction. I mean, considering friction as energy that is used that becomes converted to entropy and not like to work. If we consider statistical work to be improvement in accuracy, and then the entropy is just the variance estimator, which could be overfit or it could be inflated. So then it's like if a new observation comes in, the sort of 100% efficiency motor, it would take in 1 calorie of energy and it would translate it to 1 calorie of moving the car forward. So that'd be 100% efficiency. It wouldn't change the temperature of the environment at all. Whereas if you just burnt the calorie, the car would go nowhere and you would have released 1 calorie perfectly as heat. So there's probably some connections there with the information content of what the model is ingesting. And then it's like, is that information getting like cleanly burnt into the best possible accuracy improvement? Or is it just being like thrown away? But then it's like, what would it mean to throw it away? Like if it just didn't pay attention to the new data point and it just deleted the file in the real world, that would change the heat balance in the real world because of like the energy and information equivalences. But I don't know if that's exactly the right angle there. Okay, well, August is gone, almost. If you return at this time next week, it'll be chapter 8. Oh, let's see. This time next week, yeah, chapter 8, part 2, which everyone's welcome to join. Otherwise, there'll be another 3, and then we are on with it. But any last comments or questions?
No, just say, yeah, just thank you and see you next time.
Cool. Thank you, Frank.
Yeah, thank you.
Yeah. Thanks a lot, Daniel.
Bye.
Talk to you soon. Bye-bye.